Watch this video to prevent any plot hole in this video. If you're ready, let's get into it. Recall zeroth law of thermodynamics, which introduced us to thermodynamic equilibrium and then to temperature as T, which T not only about cold and hot, hotter than another one, or colder than another one, but now T is about quantity of hot and cold. In the future, it taught us about energy or kinematic and energy relation in our internal system. And next is the first law of thermodynamics, which introduced us to energy equation, which is rate of change of U plus rate of change of work W is equals to rate of change of heat, which is Q, about heat transfer from inner system to outer system. And then the W here is about the difference between internal and external work, or work from system or to the system. Here, both these laws is all set that tell us about process, not its direction. Why? In both laws above, heat can transfer from cold to hot. We don't care about T, so the transfer of heat can transfer from cold to hot. This statement has contradiction to experimental result. And the next one is about time translation for system, which by this some kind of symmetry, energy can go through to the past. Again, this has contradiction with experimental result. So, how we fix these two problems? Here, let's go to the history that tell us how we solve this problem. In 1824, Sadi Carnot proposed model of quasi-static process or very slow process that heat transfer from hot to cold for two platform, or we know as reservoir, with thermal equilibrium for both reservoir. To make this clear, suppose we have two platforms like this illustration, which there is T1 and T2 platform, that T2 hotter than T1, which by empirical observation, heat some kind transfer from T2 to T1. So in short, Sadi Carnot observation conclude that Q or heat transfer from hot to cold. By this result, we know about Carnot engine, that is ideal engine that has unique cycle of this engine, about Carnot cycle that is fully reversible engine, specifically heat engine. Next, in 1850 until 1854, Rudolf Clausius state that Q can transfer from cold to hot, which it seems contradict with before, but when added with W or work. This statement in modern day, it creates some kind technology as refrigerator technology. If you see in refrigerator, we can create ice inside refrigerator due to we transfer heat from inside to outside, that is inside colder than the outside. But 3 years before, Lord Kelvin has same statement, but there is a note that a machine cannot do this without W or work. This statement blocked our idealism about perpetual motion or perpetual engine, that is heat engine that can convert all heat to work, which is impossible in our modern knowledge. Then the last, in 1926, Max Planck summary all of this and then introduce us to concept about S, or we know as entropy. Wait, what the hell is going on here? Why there is S that Max Planck proposed? We're going to the next section. Second law of thermodynamics state that rate of change of entropy of universe always greater or equal to 0. And by consequence of this law, we get Clausius inequality theorem. Loop integral of delta S here is equals to 0, or the rate of change of S that create loop in some kind we call phase space is equals to 0, which by this equation, it creates Clausius inequality theorem as this closed integral which is always less or equals to 0. Here, this equation tells us that if we move S from initial, we make loop and then we back to initial, it will equal to 0, which by Clausius inequality theorem, this inequality characterized about irreversibility, which the T bath here is about temperature of our environment, or we commonly define as bath. That's why the rate of change of entropy here we can define as delta S equals to delta Q over T plus delta S from non-heat, which non-heat here is about something hidden in some literature hideout. Notice that this loop integral consequence tells us that entropy in thermodynamics is what we call state function, or tell us about state of our system, which is why the closed integral from initial state back to initial itself even with loop is equals to 0. And state function not only just entropy, there is T, S of course, P, V, and etc. You may be thinking, is this too much step forward? I understand about what you guys confused, but let me explain in simple example that Sadi Carnot do as we know in nowadays about Gedanken experiment. So let's check it out. Here's the simple example. For delta T equals to 0, or all our system here is thermodynamic equilibrium or thermal equilibrium, then our rate of change of internal energy in our system approximately is 0, which is consequence of quasi-static process for global thermal equilibrium. By this condition, we construct our system just like in this illustration, which is here T1 may be hotter than T2 and so on, and there is heat transfer delta Q here and delta W, which is net of work from our system to make our system some kind like isolate system in previous video. In this system, suppose there is no entropy because of non-heat factor, so difference of entropy here is equals to this, which is Q1 over T1 is about state of entropy in T1 and T2, the other one, so we know about S1 and S2. And because of isolate-like system, and by the first law, we can see that Q1 is equals to Q2 plus W, which then the delta S will become as this, and there is plus W over T1 here, and may be positive or negative. And here's the deal. If we know that delta W is equals to 0, then the net of work is equals to 0. So by this condition, T1 must be less than T2 to make the delta S greater or equals to 0. So here we change the index in our illustration to make consistency in our calculation, and this system is what Sadi Carnot and the next scientist think about. Why the next scientist? By same system, if W is non-zero, then we can set that T1 may greater than T2, which state transfer the heat, of course by W in here. And that's what Sadi Carnot and later scientists think about second law. As footnote in special case, if we see in entropy equality, the rate of change of entropy is proportional to delta Q over T, which here, if T approach to 0, it leads to delta S approach to infinity. But in reality, when T approach to 0, delta S approach to 0, which the energy of system to move in microscopic level get lower and lower to the some kind of ground state, which is what I say, the system is in the same state and not change, so the change of entropy approach to 0, which is this is contradiction with mathematics as in second law. So here, new law needed, which will be our discussion in next videos. And that's the second law of classical thermodynamics, its consequence and its mystery, which lead us to next law of classical thermodynamics. I hope you enjoyed this video. If you like this video, don't forget to share and subscribe. If you have any questions, please drop comment below. And that's it. See you later.